In this video we're going to look at the simple pendulum, and we're going to derive the differential equations that describe the motion of the pendulum, and we're also going to look at the period of the pendulum for some arbitrary angle, and also a simplification for small angles. Okay, so that's the pendulum there, got mass m, the length of the pendulum is L. If we drop the perpendicular, then the pendulum will make an angle theta with that perpendicular, and that up there is the fulcrum. Now the pendulum is going to swing in some kind of, it's going to swing in a circle, and if we think about the initial starting position of the pendulum as some arbitrary point, say that point there, and we'll draw a line down to the pendulum there, and if we say that the angle between the starting position and the perpendicular is theta naught, then now we can use this information here in order to derive the equation of motion of this pendulum using conservation of energy. So conservation of energy tells us that the change in the kinetic energy is going to equal the change in the potential energy. Now we'll look at both of those separately and then we'll equate them. So the change in the potential energy, so change in energy potential, well, it's going to equal the mass pendulum, gravity times the height. Now the height we're looking at is the change in height from this point here up to that point there. So the height for this at this point here, if we drop that line down, it's going to be that height there. Okay, the height at this point here, it's going to be up higher, it's going to be this height here. So the change in height is this delta H. So you can get that change in height if you take the long distance and then you take off the short distance, then you're going to be left with that height. So the long distance is going to be L cos theta, and the short distance is going to be L cos theta naught. Okay, so you have a look at the diagram and you can convince yourself of that. Okay, so that's going to be equation number 1. Now we're also interested in the kinetic energy, so the change in kinetic energy, well, it's going to equal a half mv squared, so it's a half m. Now the velocity is going to be the initial velocity, which is the velocity at that point there, minus the final velocity, which in this instance here we'll be looking at this point here. Okay, so the final velocity f squared. Now if we're saying at time t equals 0, the velocity, initial velocity is going to equal 0. We're really just saying we're holding the pendulum there, at time equals 0, the velocity equals 0, so that initial velocity is just equal to 0. So we can then say that the change in kinetic energy is going to equal a half m times the vf, which is the final velocity. So we won't bother putting the f in, okay, the f is kind of understood, so we'll just leave that half mv squared. But we've got to write that in terms of an angular velocity, okay, instead of this linear velocity v. So if we were to look at this length here, which is an arc, so that's the arc that's subtended by this angle theta, then we can say if theta is in radians, we can say that s is going to equal the length times the angle theta. Now if you're unsure where that comes from, I've got a video in this snippet section on angular displacement, angular velocity. So now if we want to find that's the angular displacement s, so if we're interested in angular velocity, we've got to differentiate that with respect to time. So that ds by dt, we just use the dot notation, where s dot is going to equal, and if we differentiate the other side of it, well, L is a constant and the angle theta has got a variation with time, so it's going to be theta dot. So we can take this here and we can replace it back into our equation for the v squared. So we're going to end up with our kinetic energy is going to equal a half m times, well, it's going to be L squared and theta dot squared. Theta dot squared. Okay, so that's number 2. So what we'll have to do is equate this kinetic energy and potential energy, which is the 1 and the 2. Okay, so we'll just do that now. So we can then say that our kinetic energy a half m L squared theta dot squared is going to equal our m times g. Now take the common factor of L out of this here, so you'll have L and you're just left with our cos of theta minus cos of theta naught. Okay, now we're interested in this in terms of our theta dot squared, which is our angular velocity, so we'll write our theta dot squared as d theta by dt. Now the m is going to cancel out. If we take the L down, then we're going to have the L at the top line cancelling with one L's at the bottom line, and we'll have to square root the whole thing. Okay, so then we're going to end up finally with our 2g upon L times our cos of theta minus cos of theta naught, and it's going to be the root of all of that. Okay, so we could call that equation number 3. Now what's that equation really telling us? It's saying that we can find the velocity of the pendulum at that point there if we were to release the pendulum from some arbitrary point up here given by angle theta naught. Okay, so it's really just saying we take the pendulum to a point theta naught, okay, the angle theta naught, and then we release it, and that equation will tell us what the velocity is of that pendulum at whatever point you choose along that curve. Okay, so that's what that is telling us. Okay, now what we're interested in is the period of the pendulum. So we're going to look at the period of the pendulum for some arbitrary starting point. Okay, so in order to get that, what we're interested in here is we can rewrite that in terms of dt. Okay, so we can find an infinitesimal change in the time whenever the angle changes, and then we can integrate up all of the angles in order to give us the complete change in time. Okay, so if we were to rewrite that equation, we could rewrite that in terms of dt, so it would be dt would equal, well, if dt goes up, the whole lot of that comes down, so it's going to be d theta upon root of cos theta minus cos theta naught. And when we take the root upon 2g, root 2g upon L down, we can, rather than taking it down underneath the d theta, we can multiply it by the reciprocal. So we can just multiply it by that reciprocal, which is going to be our L upon our 2g. Okay, now that there was just rewritten it, and as I said, that's only going to give you some infinitesimal change in time, okay, for infinitesimal change in the angle theta. So in order to find out what the total change in time is, I'll just rewrite that. It's going to be the integral from 0 to theta naught. Okay, I'll just call this, in that instance, it's going to be our value, I'll just call it a value t. Okay, so a value t is going to be the addition of all of those infinitesimal times, which occurs due to the change in the infinitesimal angle thetas. Okay, so when we integrate all that up, we get that value of t, but that's not the whole problem here, because all that's going to do is give us the factor of t for 1/4 of a period, because the period isn't just from here to here. The period is going to be from here to here, so that's one part of the period, and then the second part is up to here, the third part is to here, and then the fourth part is back to there. Okay, so we're going to have to multiply that whole thing there by 4. Okay, so that whole thing is going to be times 4. Okay, so that there is going to be a full period. So if we multiply that by 4, it's a full period, and we'll just call that big T for the period. Okay, I don't want to just keep rewriting these things out, so T. So I'll just rewrite it down, just actually this one here. So we'll have T is going to equal 4 times root L upon 2g times integral from 0 to theta 0 of d theta upon the root of cos of theta minus cos of theta naught. Okay, so that there, well, I would just put a bracket around that. Okay, and I can call that number 4. Okay, so that's given us the period of a pendulum whenever we release that pendulum from any arbitrary height. Okay, and we get the arbitrary height, and the maximum height is given by our angle theta 0. Now, it turns out that we can work out this section okay, because we've got the length and we know gravity, so we've got the constants okay, but it turns out we can knock that differential equation into a standard form, right? But the standard form turns out to be an elliptic integral, and that elliptic integral hasn't got any solution in terms of elementary functions. So what we'd do is we'd have to use some kind of lookup table for this part of that equation. So in order to find the period of a pendulum given some arbitrary start position theta naught, we'd have a constant term and then a lookup. Okay, so that's as far as we're going to go with that. Now what we're going to do is we're going to simplify it, and we're going to simplify it in terms of the derivation of the differential equation, and then we're going to look at that derivation of the differential equation and we'll simplify that in terms of a small angle. So we'll just crack on and do that just now. Okay, so this is going to be the first one was the large angle, so T. Okay, so the first part was large angle T, really there. Okay, so that's the first part, get the large angle T. Now the second part here will be in terms of a small angle approximation. So what we're going to do is, instead of looking at the equation here, which is the angular velocity of the pendulum, we're going to start looking at the angular acceleration of the pendulum, and we'll derive the differential equation from that. Okay, so to get the angular acceleration, all we have to do is differentiate this whole equation here again with respect to time. So let's just crack on, we'll get that done. So we're going to have our theta double dot is going to equal, well, we're differentiating the right hand side with respect to time, and the right hand side is, now I'll write it out in terms of 2g upon L, and it's going to be cos theta minus cos of theta naught. Now instead of putting the square root sign, I'll just put it in to the power of a half. Okay, so all we've done is differentiate that again, so theta dot becomes theta double dot, and we're just going to differentiate this side here with respect to time. So on the right hand side, what we're going to have is, it's a chain rule for differentiation, so we're going to have a half of what's inside the brackets, which is going to be 2g upon L times our cos theta minus cos theta naught, all to the power minus a half, and then we're going to have to differentiate what's inside the bracket. So what's inside the bracket, well, we're differentiating its theta, okay, with respect to time. So we're not interested in the theta naught, it's just the theta term. So it's going to be all times, well, it's going to be, cos becomes minus sine, so it's going to be minus 2g upon L sine of theta, all times, because it's the chain rule for differentiation, is going to be d theta by dt. Okay, now this d theta by dt, we've already worked out that d theta by dt. D theta by dt is this here, which is the 2g upon L cos theta minus cos theta naught to the power of a half. So that whole thing there is the same as that, only it's to the power of a half, so that will be cancel out with that entire lot there. Okay, so you can go and convince yourself of that however you look at it. The 2 is going to cancel out with this 2 here, so you're just going to end up with theta double dot is going to equal, well, I'll just take it on one side. Okay, so theta double dot, okay, and it's going to be equal to minus g upon L sine theta, so I'll take that across to the other side. So theta double dot plus g upon L sine theta equals 0. Okay, so that's a general differential equation for a simple pendulum. Now what we're going to do is we're going to simplify that. So we'll simplify it in terms of a small angle. So really what we're going to say is, if we say theta is a small angle, then we can say that sine theta is approximately equal to theta wherever theta is small. Okay, so generally say under let's say 6 degrees to 10 degrees, something about that sort of angle. Now I've got a derivation of this, sine theta is approximately equal to theta, in the snippet section, so if you're unsure where that comes from, you can look at the snippet section and that'll show you. So you can actually see it up here if you go back to this diagram. So it's really saying that whenever the angle theta is small, it's really saying that that length there is approximately equal to the curve there. Okay, that's what that's telling you. And now if the theta increases, then that's no longer the case, that length there is no longer equivalent to that curve there. So it's only at small angles that it's going to work. Okay, so we've got that simplification. So with that simplification, we can rewrite that differential equation as theta double dot plus g upon L times theta equals 0. So that's the equation that we're going to be working with now. Okay, so that's a second point of what we've got. We've got the differential equation that describes the equation of motion of the simple pendulum for a small release angle. Now I'm not going to go through all the details of the solving this differential equation. Okay, it's a standard differential equation. I'll probably do a playlist on solutions of standard differential equations, but that's for the future. But that differential equation is of the form d squared theta by dt squared is equal to k squared times theta equals 0. Okay, and the solution to that equation is going to be of the form c1 sine k of t and plus c2 cos k of t. Okay, so that there is the standard form of that differential equation, and that's the solution of that differential equation. Now if you're unsure of that, you can go and check out maybe Khan Academy videos, or check a book out on simple solutions of second order differential equations. Okay, as I say, I'll probably do a snippet section of that at some point, but there's nothing on there right now. Okay, so it means that what we can do is we can rewrite our equation out and we can pull out our value for k. So the k squared is going to be g upon L, so it means that our k is going to be equal to root g upon L. So it means that we can say that our angle theta with respect to time is going to equal some value c1 sine root g upon L times our t plus c2 cos g upon L root times our t. Now if we put in our starting conditions, and the starting conditions are d theta by dt equals 0, and theta is going to equal theta 0 at t equals 0. So it's just telling you that you're going to be starting off with the pendulum in that position there at t equals 0, and the angle theta that you're starting off with is theta naught, and the velocity, angular velocity d theta by dt is going to be equal 0 at that point. Okay, so if you go through here, and I will go through this, the differentiation of this, because it's quite straightforward. So we're differentiating that with respect to time, we're putting a value of 0 into it, and we're also just looking at that in terms of theta 0 equals 0 at t equals 0. So when you work through all of that, you're going to end up with your value theta upon t is just going to equal theta naught cos root g upon L times t. Okay, so that's our little solution there, okay, which is going to give us our angle theta in terms of our time t. Okay, so what we can then say is, if we put that in a standard form, if we look at that in terms of an angular velocity, theta t equals theta 0 cos of omega t, okay, then this value omega is 2 pi upon t. Again, if you're unsure about the angular velocity and frequency, displacement, etc., go and look at snippet section. I've got a whole half-an-hour video that explains all of that, okay, so if you're unsure of any of that. So we can then equate these here, and we can say that 2 pi upon t is going to equal root g upon L, and then we can rewrite that. We can say that t is going to equal 2 pi root L upon g. Okay, so that there is the period of a pendulum for a small angle, and it's telling you that the period hasn't got any, the mass has got no effect in the period. The only thing that's affecting the period is the length of the pendulum. Of course, gravity is a constant, so all of these are constants other than the length. So the only thing that changes the period of the pendulum really is going to be the length of a pendulum. Now we've looked at those two, so we've looked at two here. We've looked at the period for an arbitrary angle, and we've seen that it's a complicated thing because you have to use a lookup table to get it exact. And we've looked at the period given a small angle, which is a simple equation here. So if you were to go and have a look at Wikipedia, I've noted in there that it gives an example of this, and it says for an angle theta minus theta naught of 10 degrees and a value of g to, I think, 5 decimal places, 9.80665, and a pendulum of length of 1 meter, then the difference between that large angle period and the small angle period is approximately 0.2%. Okay, so not a huge difference. Okay, so that there really is the end of that part of the pendulum. Now I've actually started to do this stuff in VPython because I noticed that VPython is it's an excellent for programming, just to get a visual representation. So I've got a visual representation of this in a description of how to simulate it in VPython. Okay, so you go to the VPython, you'll have a look and you'll see that on there. Now, just